The foundry employs 215 skilled workers, specializing in alloy fabrication using over 25 advanced melting furnaces. Chemical composition is meticulously controlled through spectrometry, ensuring precise, high-quality alloy production for demanding applications. The foundry specializes in producing large castings weighing up to 20 tons, catering to heavy-duty applications. These robust castings are designed for strength and durability in demanding industrial environments. Castings can reach diameters of up to 6,000 millimeters. The foundry offers extensive on-site heat treatment capabilities, including both water and oil quenching, ensuring optimal material properties. A large inventory of casting molds supports a wide range of production needs, while specialized processes enable efficient, optimized production of small castings, ensuring precision and cost-effectiveness for diverse applications. The foundry features water and oil quenching tanks for controlled cooling processes. It specializes in spun casting tubes with diameters up to 1,000 millimeters and lengths reaching 4,500 millimeters, ensuring high-quality tubular components. The foundry provides rough machining on advanced vertical lathes, handling large castings up to 4,000 millimeters in diameter for precision shaping. The foundry offers in-house final machining using CNC machines, with vertical lathes handling up to 4,000 millimeters and parallel lathes up to 1,200 millimeters. The foundry produces high-precision parts tailored for demanding applications, ensuring exceptional accuracy and reliability for industries requiring stringent performance standards. The foundry delivers parts fully finished and ready for assembly, streamlining the manufacturing process and ensuring compatibility for immediate integration into final products. The foundry employs various control processes, including rigorous quality inspections, dimensional checks, and non-destructive testing. These processes ensure that each casting meets strict industry standards for performance, safety, and durability before delivery. Centrifugal casting is a process used to manufacture cylindrical components with a dense and uniform structure, making it ideal for producing aluminum alloy parts like pipes, tubes, and bushings. The process utilizes centrifugal force to distribute molten aluminum alloy against the walls of a spinning mold, ensuring uniformity and minimizing defects like porosity and segregation. Centrifugal casting is a technique used to manufacture high-strength aluminum alloy products, offering significant advantages in improving their mechanical properties. Laboratory number 24 at IMET Ross has developed and patented an advanced version of this process specifically for aluminum alloys. This method involves pouring molten aluminum into a rotating mold, using centrifugal force to distribute the metal evenly along the mold's walls. The spinning process expels impurities and ensures that the molten metal is packed densely, resulting in a more uniform and refined microstructure. The centrifugal casting method enhances the material's structure and density due to the gravitational forces exerted during the process. This results in improved mechanical properties, increasing the strength of aluminum alloy products by 20 to 30%. The technology is particularly suited for producing ring-shaped aluminum blanks, which benefit from the dense and even distribution of material, making them ideal for heavy-duty applications requiring enhanced durability and strength. The aluminum alloy is melted in a furnace until it reaches the desired casting temperature. Once the alloy is molten, it is poured into a rotating mold. The mold rotates either horizontally or vertically, depending on the design of the part. As the mold spins, centrifugal force pushes the molten aluminum outward, causing it to adhere to the inner surface of the mold. The rotational speed varies based on the diameter and size of the casting, but it is crucial in ensuring that the molten metal forms a dense, uniform layer. The molten metal cools and solidifies against the mold wall. Cooling rates can be controlled by regulating mold temperature and rotational speed. Since the material cools from the outer surface inward, the outer layers are dense and free from defects, while any inclusions or impurities are pushed toward the center. After solidification, the casting is removed from the mold. The inner surface, which may contain impurities, is machined to achieve the desired internal diameter and remove any imperfections. The iron ore mine is the initial stage in steel production, where raw iron ore is extracted from the earth through surface or underground mining. This ore, rich in iron oxides, is mined, crushed, and screened to produce iron ore concentrate. The ore is then transported to steel mills for further processing. At Bath Steel Company, this iron ore is a critical raw material, ultimately converted into billets, which are heated and rolled into rebars and wire rods. In the heating process, steel billets, which are solid blocks of steel, are placed in a reheating furnace to raise their temperature above 1,200 degrees Celsius, the recrystallization point of steel. This high temperature softens the metal, making it malleable for the subsequent rolling process. The reheating furnace operates on either gas or electric power and ensures uniform heating of the billets. Temperature control is critical to prevent defects in the steel structure. Once heated to the desired temperature, the billets are removed and transferred to the rolling stands, where they will undergo plastic deformation to be shaped into rebars or wire rods. Rolling stands are crucial components in the hot rolling process, where heated billets pass through a series of heavy rollers. These stands progressively reduce the billet's thickness and shape it into the desired form. Each stand applies precise pressure, ensuring uniform size reduction and elongation, transforming the billet into wire rods or rebars. Wire rod rolling is a specialized stage in the steel manufacturing process, where heated billets are progressively shaped into thin, flexible steel rods. After passing through the initial rolling stands, the billet is further reduced in size using a series of high-speed rolling mills. These mills employ grooved rolls that continuously decrease the diameter of the steel, transforming it into wire rods, typically ranging from 5.5 millimeters to 16 millimeters in diameter. The wire rod rolling process requires precise control of temperature and speed to ensure uniformity and prevent surface defects. As the rods are elongated and reduced in size, they are coiled into compact rolls for easier handling and transportation. Wire rods serve as a raw material for various industries, such as construction, automotive, and manufacturing, where they are used to produce wires, fasteners, springs, and welding electrodes. High-quality control ensures the wire rods meet specific mechanical and chemical property standards. The process begins with heated billets, which are passed through multiple rolling stands, each progressively reducing the billet's size and shaping it into the desired form. The rolling stands apply significant pressure as the steel billet is elongated and flattened into a cylindrical shape, while ribbed patterns are simultaneously rolled onto the surface to improve the rebar's bonding with concrete. Rebars are typically rolled in diameters ranging from 6 millimeters to 40 millimeters, depending on their intended use. The ribbed pattern, either helical or straight, increases the mechanical adhesion between the steel and concrete, concrete, ensuring that the structure resists cracking and maintains integrity under stress. Temperature control during the rebar rolling process is essential to prevent defects such as uneven thickness or poor surface quality. After rolling, the rebars are cut to specific lengths, cooled, and inspected for quality. These rebars are critical for reinforcing concrete in various construction projects, including buildings, bridges, and infrastructure, providing enhanced tensile strength and durability. The CNC Full Automatic Hot Spinning Machine 2 Rollers Hot Spinning Machine is a highly specialized piece of manufacturing equipment designed to shape metal into precise cylindrical or conical forms through hot spinning. This technology is widely used in industries such as automotive, aerospace, defense, and energy, where the production of hollow, seamless components with high strength and durability is critical. The machine is fully automated with a computer numerical control (CNC) system, allowing for high precision and repeatability. The CNC control ensures that the spinning process is carried out with accurate measurements and control of parameters, such as feed rate, speed, and pressure, which are crucial when working with high-temperature metals. This machine is equipped with 2 synchronized rollers that exert pressure on the metal workpiece, gradually shaping it as it rotates. The 2-roller system allows for more efficient material deformation, reducing the number of passes required and improving overall production speed. Unlike cold spinning, hot spinning involves heating the metal workpiece to its plastic deformation temperature, which allows for the formation of more complex shapes and ensures better mechanical properties in the final product. Hot spinning is particularly useful for working with tough or hard metals like titanium, stainless steel, and Inconel. The hot spinning process minimizes material waste since the metal is formed through controlled deformation rather than cutting. This is especially valuable for expensive or hard-to-machine materials. The CNC Full Automatic Hot Spinning Machine is used to manufacture a wide range of components such as pressure vessels, gas cylinders, automotive wheel rims, and aerospace parts. Its flexibility in handling different materials and shapes makes it a versatile tool for various high-precision manufacturing needs. Centrifugal casting is a manufacturing process that utilizes centrifugal force to create cylindrical components like sleeves, bushings, rings, and cylinders. The method is particularly well-suited for producing items with a fine and uniform grain structure, leading to enhanced mechanical properties and high integrity in the final product. In this process, molten metal is poured into a rotating mold. As the mold spins rapidly around a central axis, centrifugal force pushes the molten material toward the mold's walls, ensuring that any impurities are forced toward the inner surface, which can be machined away after casting. This spinning action promotes the formation of a dense, fine-grained microstructure, resulting in parts with superior strength and durability. The centrifugal casting method is highly versatile, allowing the use of various materials depending on the application. Common materials used include nickel-based alloy steel, heat-resistant steel, stainless steel, cobalt-based alloy steel, and duplex steel. These materials are selected based on the component's required properties, such as resistance to wear, corrosion, or high temperatures. The technique offers several key advantages. The continuous rotation and force applied during the process reduce porosity, eliminate gas bubbles, and create a homogeneous structure across the material. This results in products with minimal defects, making them suitable for critical applications in industries like aerospace, automotive, and power generation, where structural integrity and durability are paramount. Centrifugal casting is particularly beneficial for producing hollow, cylindrical parts, as it is more efficient and economical than traditional casting methods for these geometries. Additionally, the ability to control the wall thickness and internal dimensions makes the process flexible, enabling manufacturers to create customized components with precision. Train wheel manufacturing is a highly automated and precise process involving several key stages that combine cutting-edge technology with powerful industrial machinery. One of the first steps in the process involves the loading manipulator, which positions raw material, typically steel, onto the production line. The press dies play a crucial role in shaping the initial raw material into the desired wheel form. During the blanking phase, a sliding table moves into place, and the press exerts a massive force, around 9,000 tons, to upset the blank, ensuring it begins to take the general shape of a wheel. This part of the process is essential for setting the profile blank that will undergo further refinement in the rolling phase. Train wheel manufacturing is a highly automated and precise process involving several key stages that combine cutting-edge technology with powerful industrial machinery. One of the first steps in the process involves the loading manipulator, which positions raw material, typically steel, onto the production line. The press dies play a crucial role in shaping the initial raw material into the desired wheel form. During the blanking phase, a sliding table moves into place, and the press exerts a massive force, around 9,000 tons, to upset the blank, ensuring it begins to take the general shape of a wheel. This part of the process is essential for setting the profile blank that will undergo further refinement in the rolling phase. Once the wheel blank is formed, it is removed by the first transfer manipulator and moved on to the next stage of the process. Here, 3 industrial robots take over, cooling and lubricating the press dies automatically. These robots are equipped with DNC-controlled axes, allowing them to operate with extreme precision, enhancing the consistency and quality of each wheel produced. At the rolling stage, the wheel blank is guided by web rolls, a pressure roller, and lateral rolls without a mandrel, a cutting-edge feature of state-of-the-art wheel rolling technology. The absence of a mandrel improves efficiency and reduces wear on machinery. Furthermore, the material flow during rolling can be optimized by making corrections to the tool settings online. This dynamic adjustment capability ensures that any minor deviations in the rolling process are corrected in real time, ensuring the final product meets stringent quality standards. To further maintain precision and quality, the press dies undergo automatic cooling and lubrication, ensuring they operate efficiently without overheating or excessive wear. An oscillating needle embossing tool is then used to mark the wheel with identification text. This is done through a needle embossing device that works with high accuracy to ensure every wheel is correctly identified and tracked throughout the manufacturing process. After marking, the wheel moves to the wheel measuring machine, which employs the latest 3D laser technology to measure its dimensions and confirm they align with the required specifications. This step is crucial for ensuring the wheel meets safety and performance standards, as even small deviations in size or shape could impact its performance on the rails. The world of machining is undergoing a significant transformation, and the Rivet CNC lathe is at the forefront of this innovation. This compact, user-friendly device combines cutting-edge technology with a console gamepad control, offering unparalleled precision, ease of use, and safety. Ideal for both professional and hobbyist applications, Roan's size and capabilities make it a game-changer in the CNC lathe industry. Big innovation in a small package designed to fit on any desktop, the Rivet CNC lathe is small in dimensions, but mighty in performance. Despite its compact size, it provides a robust solution for crafting a variety of materials with remarkable precision. Whether you are shaping steel, aluminum, brass, plastic, or even wood, Rivet can handle materials up to CK45 hardness. The compactness of the lathe makes it an ideal tool for users with limited workspace, but its versatility ensures that the lack of space does not mean a compromise in performance. Versatile material capabilities. One of the standout features of the Rivet lathe is its ability to cut and shape a wide range of materials. This opens up endless creative possibilities for users, from from intricate jewelry designs to robust mechanical parts. Whether you're working with hard metals or softer plastics and woods, Ront handles them all with precision, giving you the flexibility to bring your ideas to life with ease. Additionally, the machine's accuracy, up to 0.02 millimeters, ensures that your projects are of the highest quality, delivering professional-level results regardless of the material. A new standard in safety is a primary concern when it comes to CNC machinery, and Ront addresses this with its innovative protective skin technology. This feature ensures that users can operate the lathe without the risk of injury, even when controlling it via the gamepad or touchscreen. Unlike traditional lathes that may expose users to flying chips, greasy residue, or other hazards, Ront guarantees a safe and clean working environment, making it ideal for users of all skill levels. Touchscreen and smart app control. Ront provides an intuitive user experience with its spacious 7-inch touchscreen, which gives access to all machine functions. The screen displays vital data such as rotation speed, feed rate, and usage time, offering complete control over every aspect of the machining process. The touch interface also provides an easy manual control mode, enabling precise adjustments during operation. The flexibility doesn't end there. All touchscreen features can be accessed via a web or mobile app, ensuring that users have full control of their lathe, whether they are in the workshop or working remotely. This combination of touchscreen, app control, and gamepad functionality makes Ront one of the most user-friendly CNC lathes available today. Gamepad compatibility. For a smooth experience, a standout feature of the Ront CNC lathe is its compatibility with console gamepads. This innovation allows for smooth and precise control, akin to operating a scalpel. The gamepad control makes the machining process more accessible and intuitive, especially for those familiar with gaming devices. This unique feature not only enhances precision, but also adds an element of enjoyment to the machining experience, offering a modern twist on traditional machining methods. Despite its powerful capabilities, the Ront lathe operates with minimal noise, producing only 60 decibels A during idle and 75 decibels A when machining parts. With Ront's precision and ease of use, the creative possibilities are endless. Forging is a crucial process in the manufacturing of parts for couplings and buffers of railway vehicles, ensuring that these components are strong, durable, and capable of withstanding the mechanical stresses encountered during operation. Couplings and buffers are vital for railway safety, as they are responsible for connecting rail cars and absorbing the impact forces during train movement, starting, stopping, and in cases of collision. The forging process typically involves shaping metal, steel, by applying compressive forces at high temperatures. This method enhances the mechanical properties of the material, resulting in components with high strength, toughness, and resistance to fatigue and wear. These attributes are particularly important for railway parts, as they operate in harsh environments and under significant mechanical loads. Forging for railway couplings and buffers usually begins with selecting high-quality steel, which is heated to a temperature where it becomes malleable. The metal is then shaped using large industrial presses or hammering machines, which mold it into the desired forms. After the initial shaping, the parts may undergo further machining or heat treatment processes to refine their dimensions and enhance their mechanical properties. Heat treatment, such as tempering and annealing, is used to improve the toughness and hardness of the components, making them more resistant to cracking and deformation under stress. A hydraulic rivet setting machine is an essential tool in assembling truck frames, especially in cold riveting processes. Riveting is a common technique in manufacturing truck frames due to its ability to create strong, durable, and reliable joints that can withstand heavy loads and stresses. Cold riveting versus hot riveting. In the context of truck frame assembly, there are two primary riveting methods: hot riveting and cold riveting. Hot riveting. This process involves heating the rivets until they become malleable, then using pressure to shape the rivet head. The advantage of hot riveting is that the metal, when hot, is easier to deform and mold into the desired shape with less pressure. However, the residual stress in the rivet head is lower because the metal is more relaxed when hot. Despite the advantage of easy deformation, thermal expansion and contraction can create internal gaps, leading to a weaker joint. In addition, hot riveting may allow some components to be removed easily, which may not be ideal for truck frame stability in the long term. Cold riveting. This process, often done with a hydraulic rivet setting machine, does not involve heating the rivets. Instead, high pressure is applied to deform the rivet through a process called cold flow, where the rivet material flows into the gap between the equipment and the rivet hole. Cold riveting produces greater stress in the rivet head, resulting in a stronger and more durable joint. It eliminates gaps between the rivet and the equipment, ensuring uniform pressure distribution and better strength consistency. This makes cold riveting preferable for truck frames, where strength and uniform load bearing are crucial. The hydraulic rivet setting machine is particularly advantageous for cold riveting. The machine uses hydraulic pressure to deliver the high force needed to deform the rivet in the cold state. This results in stronger and more uniform joints, with no gaps that could weaken the structure. Additionally, the machine allows precise control over key parameters such as pressure, time, and force, ensuring high quality and consistent rivets.